Okay, welcome back, Regents physics students. This is the 8th and final lesson of the waves unit. So here we are at the end of the unit. It's on what's called the Doppler effect or the Doppler shift. So if you have not seen the video that I included in this assignment already, pause this video and go and watch the video, because it's better this time to see the effect first before I talk about it. In the effect, you'll see a car horn honking as the car comes toward you and then it passes you, and then the other one is with a train. And the train one is nice because it shows some diagrams of wave fronts that are really kind of illustrative of what's going on. I'm going to try and draw those things later, so if you see them in the video, it'll be easier to understand when we're drawing them. So the Doppler effect or the Doppler shift, as you saw in the videos at this point, is the shifting of a sound pitch. In other words, the frequency you observe in any wave because of motion. And the videos, for some reason on YouTube, always focus on the motion of the source. The car driving by you, the fire truck, the ambulance, the train. And that makes a higher pitch, a higher tone when the car is coming toward you than when the car's going or the object is going away from you. That makes a lower tone. But the Doppler shift can happen not just when the source of the wave moves, but the observer also. And for some reason I couldn't find videos of that. In the class back at school, I have a laser disc, which is basically a DVD, like, giant DVD. So I have it of a train moving past things that make noise. And so we could see the observer moving, but unfortunately I don't have that here. So first thing we're going to talk about is why that happens, what causes it, and we're going to learn a formula how we can calculate the change or the new frequency that's observed because of the motion of either the source or the observer. Before we do that, I want to just remind you what a higher pitch is. A higher pitch is not a louder sound. It's a sound that's more toward the squeaky range. Like if I take this glass and I flick it, I can't sing that note, right? That's really high and squeaky. Maybe an opera singer can. But that's what we mean by a higher pitched, a sound that turns more like this. A low sound would be, imagine a bass guitar in a band and they strike the note and it's that low rumble, or thunder rumbling, right, like that. That's a lower pitch. It doesn't mean it's loud or quiet, lower pitch. It just means the tone of the sound. Okay, so that's higher, lower pitch. The first thing that can happen for the Doppler shift is, as we have a speaker making compressions and rarefactions, I didn't label the rarefactions, and the wave is moving like this, we have an observer that's getting hit by these compressions, and they're hitting the observer's eardrum. And based on the frequency that the drum is being hit, that's the tone that the observer perceives. If the observer comes toward the compressions and starts running this way, you might imagine the compressions coming this way and the runner's running this way. He's going to run past the compressions at a higher frequency. They're going to strike his ear instead of like this. They're going to strike it more rapidly and he's going to hear higher tone. If the observer runs away from the speaker, then you might imagine as you're running away from this way, the compressions are going to hit you, instead of at the original, they're going to hit you slower because you're sort of running away from them, so it takes them longer to get to you. So that's a lower pitch. Higher pitch run towards, lower pitch run away from the speaker. So this is what this is saying, just written out. Okay, so not louder, just a bit closer to a squeak. This is not quieter, just a bit closer to resembling thunder. Okay, so that's the observer moving. The videos, as I mentioned, show what happens when the source of the sound, the speaker, the car horn, the whatever it is, it could be a light, okay, light bulb coming toward the observer. What happens? With no motion, what happens is the waves spread out concentrically. Imagine that I'm dropping or I'm tapping water like this, and the circular waves are spreading out like this, and I'm tapping at a steady pace, so we have all these concentric waves. The rate at which I'm tapping, those are the same frequencies observed by observer A and observer B. So A and B observe the same frequency as the source when there's no motion. But if the source starts moving, so instead of tapping in one spot, well, maybe it's a bug that landed in the water and is flapping its wings to try and get out, and then it starts swimming while it's tapping its wings. What happens is the first circle is centered here where the bug was originally, but each circle is centered more and more to one side because the bug is moving as it creates every next wave. And what that does, as you saw in the videos, it makes the waves in the front of the object, it's moving this way, pile up and get squeezed together, the compressions of the sound waves. And back here, it makes them stretched out compared to the original, again, because of the motion. So observer B over here, with a smaller wavelength, observes a bigger frequency. Remember, V equals lambda times frequency. And so V equals lambda times frequency, right? If I just drop that down. This is the speed of sound in the given conditions. Maybe it's 331 at STP. When this gets smaller, that has to get bigger, so we have the same equation preserved. So the shortening of the wavelength here means a bigger frequency. Back here, stretched out wavelength, smaller frequency. And that's what we saw with the trains and the car horns. Higher tone as the car is coming toward you, and then a lower tone when the car goes away. There's an equation that allows you to calculate the new frequency that you observe. Okay, so here it is. F observed is F, the frequency of the source, the speaker, the siren, whatever. This here is the speed of sound in the top and bottom, plus or minus, top and bottom, observer and source speeds in the formula. So let me do an example calculation. So let's see. Okay, that'd be about here. So cops are driving 50 meters per second. That's like over 100 miles an hour. But they're chasing the robber driving away 40 meters per second. Okay, so they're gaining on the robber. The siren is 500 hertz at that instant. That's at the speaker. That's what it's creating with its oscillations. The speed of sound on the day is 340. Determine the frequency the robber hears. So we use our Doppler formula. And what we have here is the original frequency, the speed of sound, and then this is the observer, the robber. He's hearing the siren. This is the source, the siren itself of the cop, okay, moving at 50 meters per second. Now, I didn't fill in the plus or minuses because this is where you have to do some thinking. Based on what we know that when an observer goes away from a speaker, like over here, they're going to encounter the compressions at a lower rate, so that means moving away creates a lower frequency. So we go back to our calculation over here, and we have to decide, what do we put in here, a plus or a minus, to make the answer come out smaller, which is what we know the concept to be for the Doppler effect. And what we have to put in to make the answer smaller is we've got to put a minus sign here. Because if we put a plus, this will make this numerator bigger. It'll make it 380 instead of 340, which will give us a bigger answer. We're going to make it 300 by putting a minus there. So that's how you figure out that a minus goes there. The cop moving 50 towards the robber. You have to remember, what happens when a speaker moves toward the observer? We have that over here, right? So we saw that as the speaker's moving toward, it's going to cram the wave fronts together, make a higher frequency. So that 50 has to enter into the calculation to make a bigger answer. How do we make a bigger answer? We don't put a minus here because that's going to make a smaller denominator, which will make a bigger answer. So what we need is a bigger denominator. We need a smaller numerator and a bigger denominator. So this 50 makes for a bigger denominator. Sorry, that I have it backwards. So The 50, we want this to be a bigger answer. If we put a plus, we're going to make a bigger denominator, smaller answer. We need to put in a negative to make a smaller denominator to make a bigger answer. So sorry about that. Hopefully that didn't confuse you. But again, you think about what this 50 should be doing to the answer, and then you put in a corresponding plus or minus to make that 50 do the right thing conceptually. Increase the frequency, so it has to make the denominator smaller. So what we have is, if we just simplify 300 over 290, which slightly increases the frequency from 500 to 517. All right, so that's a calculation example. I just want to briefly mention that there are other examples of the Doppler effect that you need to be able to identify. Like, for example, police radar guns. You're driving down the road, and maybe you're going 20 miles over the speed limit. The cops pull you over. How did they figure out what speed you were going? Obviously, they don't have a way to look at your speedometer. What happens is they have these things called radar guns. They send out electromagnetic waves. You can't see them with your eyes, right? So, and then they hit your car and they reflect. And based on how fast your car is going, it's going to shift the frequency a certain amount. And so the police officer, the gun will observe a different frequency than the source reflecting off your car, and that depends on the relative velocities of the police officer and you, and the software can calculate from these frequencies how fast you are moving. So it's all done by the Doppler effect. Doppler radar for clouds, they can figure out whether a cloud is moving toward a weather station or away. And again, maybe you could look at it and just figure that out with your eyes, but that's not going to be very accurate. So they send radar at the cloud, and what reflects will tell by the frequency change compared to what they've sent out, what reflects back, the change. The software can calculate how fast the cloud is moving and in what direction. The final thing I want to mention, an example of the Doppler effect, is redshift of starlight, proving the universe is expanding. So astronomers can look out at the stars in the sky, different faraway galaxies, and we know the frequencies that starlight should be sending out. That's well understood from the kinds of nuclear reactions that are happening in the stars. And what they notice is that those light frequencies, instead of being what we expect from the theory, are shifted to a slightly lower frequency. It doesn't mean the stars turn red. It means that they're just turned a little bit lower frequency, a little bit toward, they shift a little bit toward red, which is lower frequency light. And so that is proof that the galaxies that they were looking at were moving away. If they were moving toward us and they were going to like maybe crash into our star or something, then they would be moving toward a higher frequency. It'd be a blue shift for the starlight. But it's not. It's red shift. The star is moving away from us. Doppler effect. So that's the Doppler effect. That's it for topics in the wave unit. And so just complete the homework, and we'll move on to the next topic shortly, in a couple days. Okay.